So thank you so much. It's really a great pleasure and a great honor to be here celebrating Rick's birthday. His work has been hugely influential to me and many others. The work I talk about today is not I won't be able to actually cite one of Rick's papers, but we will be relying very much, we're inspired very much by a construction of Folter, Glick, Piliavsky, and Ramasamy, at least one of whom is a Rick acolyte, so I think that's almost as good. So the work I'm talking about is joint work in progress with Chaim Even-Zohar, Matteo Parisi, Melissa Sherman-Bennett, and Ran Tessler, and some of the results I will mention were prior work additionally joined with Spiegel-Leclerc. I seem to be the first old-fashioned Blackboard speaker here today. I hope I can shame some of you into giving Blackboard talks in the next days. Or maybe this will be a disaster and then you'll do the opposite. So here's the outline of my talk. I'm going to briefly review the notion of the positive Grassmannian and the amplituhedron. The amplituhedron we saw in Pasha's talk yesterday, although I don't think we actually saw a definition, so I'm going to give you a definition. I'm then going to tell you about the notion of vector relation configurations, which were developed in a paper of AGPR. And then I'm going to present our new main construction, which is the construction of something we call Plabic tangles. And they're a bit inspired by von Jones' planar tangles, but we're using Plabic graphs in them. And then I'm going to explain how these are related to cluster quasi-homomorphisms and cluster adjacency for the amplituhedron. So somehow the amplituhedron was the motivation for all of this setup, but we get applications to the cluster structure for the Grassmannian. And so before I begin for real, I just want to make a remark that Plabic graphs, or planar bicolored graphs, the graphs we saw in David's talk in the last hour, and here I'm talking about embedded in a disk. These have traditionally been used for a couple of, in a couple of ways. One is one can use them to define subsets of the Grassmannian, whether it's positroid cells or positroid varieties. Something else one can do if you have a Plabic graph that can be viewed as a web or tensor diagram, you can use them to define functions on the Grassmannian. But now what we want to do today is explain how to use Plabic graphs with a slight enrichment to define maps between Grassmannians. And we realized that one could do this in the process of understanding the cluster structure on the amplituhedron. Okay, all right, so now let me give some definitions. So the Grassmannian, GRKN, is the set of k-dimensional subspaces of an n-dimensional vector space. And I'll mostly be working over C today, but sometimes over R. We will represent elements as row spans of matrices A, where A is a k by n full rank matrix. And I want to introduce Plücker coordinates. So if capital I is a k element subset of the numbers 1 through p sub I, then p sub I of A, the Plücker coordinate, is the determinant of the submatrix of A located in columns I. Okay, and now the positive Grassmannian, I mean, really to be precise, I'm going to define the totally non-negative Grassmannian. This is the subset of the elements in the real Grassmannian where Plücker coordinates are non-negative for all k element subsets of 1 through n.
Excuse me, Lauren.
Mm-hmm.
Could you please raise the board?
Oh, yes. Raise this board right here?
Yeah.
Okay. 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 And I'll just mention that this notion of positive Grassmannian first appeared in works of Lustig and Postnikov. And really the only point about it that I want to mention for today is that if we partition the positive Grassmannian into pieces based on which Plücker coordinates are strictly positive versus equal to 0, we get a cell decomposition into cells where G runs over equivalence classes of certain planar, and for today I'm mostly going to say bipartite graphs. Okay, and this is okay. So that's it. We have this positive Grassmannian, and one can partition it into cells, and the cells are indexed by certain planar bicolored graphs. Now, we heard about scattering amplitudes and the amplituhedron a bit in Pasha's talk yesterday. Pasha said the word amplituhedron many times without defining it, as far as I recall, so I'm going to define it. So this is a definition of Arkhani Hamed and Trinka. So they were motivated to give a geometric framework for the BCFW recurrence for scattering amplitudes in n equals 4 super Yang-Mills. And they wound up introducing the following object. So let's fix k and m with n at least k plus m. And let's choose a matrix, Z. It's going to be an n by k plus m matrix with maximal minors positive. And now we get a map that we'll call Z tilde from the positive Grassmannian of k planes in n space to the Grassmannian of k planes in k plus m space. And on the level of matrices, this map is simply matrix multiplication. So take a k by n matrix representing a point in the positive Grassmannian, and now let's just do matrix multiplication by Z. So A is k by n, Z is n by k plus m. So we get a k by k plus m matrix. A lemma one can prove is that this matrix has full rank, and hence it represents a point in this Grassmannian. So we're always going to be identifying matrices with row spans. So this is a map, and now the tree amplituhedron A, N, K, M is the image of the positive Grassmannian under this map. And just to compare with Pasha's talk, so in Pasha's talk, he was secretly fixing m equals 4, but he was also allowing something called loops. So I'm going to be talking about the tree amplituhedron, but I will talk about it for arbitrary positive m.
What does the matrix Z have to satisfy that max minus?
So this is so n is at least k plus m, and so I can look at all k plus m by k plus m submatrices, and I require their determinants are positive. Yeah, and that's, yeah, so the positivity of z and the positivity here both get used in checking that this map is well defined. Okay. All right. So now I can forget about reals, and I can give a kind of algebraic version of this story. So let's take k and m as above, and let's let z just be an n by k plus m matrix with maximal minors non-zero. And then we have a rational map, which I'll still call z, from the Grassmannian. Okay, but this is rational, so let me make this as a dotted map to the Grassmannian of k-planes in k plus m space. Okay, so let me write down some questions that one can ask, which were motivated by the questions from scattering amplitudes. So for fixed positive m, when is z tilde injective on a cell of the positive Grassmannian? And why might we care about this? So let me just point out that this Grassmannian here has dimension k times m. This positive Grassmannian has dimension k times n minus k. By our constraint that n is at least k plus m, this dimension is in general bigger than this dimension. So this amplituhedron is defined as the image of a surjective map, which in general is far from being one-to-one. But the notion of triangulation or tiling, which came up in Pasha's talk, is asking about the following question: can I cover the amplituhedron, which lives in this Grassmannian and has dimension k times m, using images of k times m dimensional cells here? And in particular, we would like to restrict to such km dimensional cells here where the map is injective. Okay, so that's where this question is coming from. Now there's also a kind of algebraic version. Yeah, so n equals k plus m is kind of boring because then z we could take to be the identity, and we recover the positive Grassmannian as a special case of the amplituhedron. Uh-huh. Yeah. So there's a slightly more complicated of loop amplituhedron where you're not just looking at the, you don't just have the image of this positive Grassmannian, but you also have some extra lines floating around. But yeah, I don't really want to go into that definition. Uh-huh.
Well, what confused about the phrasing of question one is that you just explained the connection that the drawing is supposed to be for all the cells or all correct dimensional cells.
This question one? No, I'm just asking when is, well, so let's say when is z tilde injective on a km dimensional cell?
Oh, on AKM.
Yeah. I mean, Yeah, I mean, the answer to the question is easy if the dimension is bigger than k times m. Yeah, and we'll be most interested in the case where they have km dimension. Okay, so we can let pi g be the Zariski closure of S sub g. This is called the positroid variety and was studied in a nice paper of David with Allen and Thomas. And we can now ask in this setup, when is our amplituhedron map generically one-to-one on this positroid variety? And if this happens, I will write INTM of g equal to 1 and say that pi g has intersection number 1. Okay, so INT is for intersection number, and I want to always remember this number m, which is a key component in the definition of this map z tilde. Okay, and then another question is, how can we describe the boundary of a given cell, of the boundary of the image of a given cell, particularly when our cell is a cell on which this map is injective. And conjecturally, this boundary is cut out by compatible cluster variables of the Grassmannian. Yeah, so there was a conjecture called cluster adjacency coming from scattering amplitudes, which says that when you write down the terms of the BCFW recurrence, you get this sum of rational functions, and in every term, what you see in the poles is compatible cluster variables. And so using this kind of framework, we proved that in the m equals 4 BCFW setup, but one can ask this question for any m. And so that's what we would like to understand. Okay, so now I want to explain the construction of vector relation configurations. Oh, maybe I should be raising boards. Can people in the back see this board? Okay. Okay. Okay, so the vector relation configurations, as I mentioned, were developed in this paper of Folter, Glick, Piliavsky, and Ramasamy, and actually were closely related to a construction from Arkani Hamed, Borgeli, Kachazo, Gontroff, Plotnikov, and Trinka. So let's see how this goes. So let's let G be a bipartite planar, which I'll abbreviate as Plabic, graph in a disk with black and white interior vertices, which I'll denote by B union W. Sorry, let me just say, with black and white vertices labeled B union W and edges E, and where the boundary vertices B sub boundary are black and labeled from 1 to n. And I also want to fix a positive number m. Let me draw this picture. So here's one of my favorite Plabic graphs. I guess it's going to look a little bit boring. It's a tree. And now an m vector relation configuration, which I will abbreviate by MVRC on G, is an assignment of vectors VB to each black, to every black vertex in the picture. Oh, and VB I want to lie in CM. And edge weights to each edge in the picture such that the boundary vectors V1 through Vn span C to the M, and for each white vertex W, we have a relation. So R sub E, V sub E is 0, and this is for all black vertices incident to the white vertex. Okay. And so let me give my notation here. So we will write BR, which is my collection of vertices and weights on edges for an M VRC. And the boundary of my vector relation configuration is the M by N matrix of boundary vectors, which I will denote by boundary of VR is V1 through Vn. Okay. So this is just reading off the vectors around the boundary of the disk. Okay. Now, as we've seen in David's talk, we have gauge transformations. And also an action of GLMC everywhere. And just to show you what the gauge transformations look like here, whenever I have a white vertex, if I look everywhere around it, say these weights are R1, R2, R3, I can always rescale by some complex number, T. And one still, if you had a relation among the vectors at these, sorry, I'm calling these black vertices. This is a black vertex. This is a white vertex. So if you had a relation in this setup, then you still have a relation over here. And also, for every internal black vertex, sorry, I should probably just say shaded vertex, then I can do a gauge transformation as follows, where I rescale both the weights on the edges and also the vector. So TR1, TR2, TR3, and then I will scale my black vector in the middle by 1 over T. Okay. So whenever we talk about vector relation configurations, we will be talking about them up to gauge. Okay. So now let's go back to the small example that I wrote down. So, okay, let me just draw this again. Let's call this black solid vertex here B2 and this B1. Okay, so we're going to suppose that VA, VB, so my boundary vertices, for various reasons, I'm just going to call A, B, C, D, N. Are generic vectors in C star to the 4. So I'm going to choose here m equals 4. Then this B1, C, and D all surround a white vertex, a hollow vertex, so they satisfy a relation. So do VB2, VA, and VB, because B2, A, and B surround this white vertex. And also VB1, VB2, and Vn satisfy a relation. And okay, I will try to speak loudly. So we see that VB1 must be in the span of VD and VC, and also the span of VA, VB, and Vn. And because this is a 2-plane in C4, and this is a 3-plane in C4, this intersection is a line in C4. And similarly, VB2 is in the span of Vn, Vd, Vc, intersect VA, VB. And for the same reason, this is also a line in C4. And so we can choose, e.g. the representative VB1 equals determinant of A, B, C, N, Vd minus determinant of A, B, D, N, Vc over A, B, C, N, where my notation A, B, C, N means the determinant of VA, VB, VC, Vn. Okay. And similarly, we can choose a representative VB2, which is ABCD Vn minus ABCN Vd plus ABDN Vc over ABCD. Okay. So in this way, we can actually work out the entire vector relation configuration, including the weights on edges. Okay. So any questions about this vector relation configuration? And can people in the back still hear me, or should I? Maybe people can come a little bit forward if there are available seats, but I will also try to speak loudly. Okay. All right. So,
there's also a handheld mic.
oh, yeah, I could do that actually. Where is it actually? I'm writing on the board, but I can possibly hold my notes and microphone at the same time. Is that better? Yeah? Okay. Okay. Actually, this is a little bit tricky, but let's see how it goes. Okay. So the question that we want to ask now is, when can we uniquely reconstruct the interior of a vector relation configuration from the boundary? And okay, so this is the question I'm going to write down is related to, but not exactly the same as a question that was addressed in the AF GP paper. So we will say that a Plabic graph G is M generically solvable if for generic boundary vectors v1 through vn in CM, there exists a unique M vector relation configuration up to gauge and GLM action. So the question, of course, is when is G M generically solvable? And the key question, the key point I want to mention here is that what I care very much about these n vectors as having no relations among them. I really want these to be n vectors in CM with non-vanishing Plücker coordinates. Okay, so here's the first theorem. Is the microphone working fine for the back? Okay. So the first theorem is that G is M generically solvable if and only if our positroid variety, or equivalently the positroid cell, has dimension k times m, and pi g has intersection number 1. And so what I want to point out is that this answer to a question motivated by physics, namely this question about positroid varieties having intersection number 1, or positroid cells mapping injectively into the amplituhedron, the answer to this question is the same as the answer to the question of when can you uniquely reconstruct the interior of a vector relation configuration from the boundary. Okay, and just to make a few remarks, there's a theorem of AGPR, which maybe at first glance looks related, and it has some overlap with this. So there's a theorem of AGPR which says if you start with some positroid variety pi g and put elements of ck around the boundary representing an element of that positroid variety, then we can uniquely solve for the interior when G is reduced. So it's a different starting point in our two setups. In our setup, we have our positroid variety lying in GRKN, but we choose another number, M, and we put generic boundary vectors from CM, and then we try to reconstruct the interior. Whereas in their setup, they are putting elements of, they have their same positroid variety in GRKN, and they put elements of CK around the boundary, but those elements of CK, these are not generic vectors, but rather represent an element of this positroid variety. And so our theorems overlap exactly in the case when n equals k plus m, which is the case when the amplituhedron is the positive Grassmannian. Okay, all right, so that's the first statement. And we have another theorem, which I probably won't be able to, well, which I might state at the end if there's time, which is that when G is a tree, we can give a purely combinatorial criterion for generically M-solvable, i.e. intersection number 1. Okay, all right, so this is all about vector relation configurations and reconstructing the interior. But now I want to talk about this notion of Plabic tangle. And this Plabic tangle is going to use the data of a Plabic graph together with some additional disks that we put in the interior of the faces. And each disk is going to represent a copy of a little Grassmannian. So if you're familiar with Plabic graphs in a disk, you know that the n boundary vertices tell you about the n in a copy of GRKN. But now we're going to put more disks inside faces of our Plabic graph. Those small disks in the faces will also have their own boundary vertices, and each one will represent a copy of a Grassmannian as well. Okay. And as I mentioned before, this framework is inspired by the notion of planar tangle as developed by von Jones. So a Plabic tangle is a Plabic graph G. So we have our black and white vertices. We have our edges. And this Plabic graph is going to be called the core, drawn inside an input disk together with L output disks, which we also call blobs, each in some face of G. And each output disk will have has its own boundary vertices, D upper I, for I between 1 and L, and each vertex of one of these output disks is connected to one element, B sub u of B, via a segment such that the resulting graph is planar. All right, so now let me go to my first example, and I will start decorating it. So this, what I've drawn in white is called the core, but now I want to stick in a blob. So in red, I will put my blob, and I'm going to connect it. So the blob is going to have its own boundary vertices, and I'm going to connect them like this. Okay, and maybe I will label these like 3, 4, and then there will also be some internal labeling 2, 3, 4 up through some, up through some n prime. Okay, so now I want to use this information of vector relation configurations. Okay, just one other remark. When I have a core and a blob, so every time I have a disk, I want to record how my boundary labels are ordered. So my core here has boundary vertices 1 through 5, and I'm going to put a star right before the 1, just to indicate that this is where our numbers started in order. And on this output disk, on my blob, I'm also going to have a star just to record where where my labeling begins. Okay. All right, so now how do we define a map? So first, yeah, and okay, the point is if I want to write down, so if I have a vector attached to each one of these boundary vertices, I just want a way to write down those vectors in order to give me an m by whatever matrix.
So the red 3 and 4 are also vertices of the original graph?
No, no, they're boundary vertices of the blob.
But the other, the ones on the boundary.
Oh, yes, yes, yes. Yeah, yeah, I should have.
Yeah, 3, 4, 3, 4.
Yeah. And in fact, I should really use a new label set for the blob, but it's convenient to just label boundary vertices in order.
Are there additional vertices inside the blob?
No. Inside the blob, this is just a sort of empty disk. But the point is, with these kind of tangles, you can compose them. So I could stick another tangle inside this blob to compose maps. Uh-huh.
So you don't mean to, I mean, there's two white vertices also called 3, 4, but those are just a.
It's 5 and 6.
Oh yeah. Okay. So let me do this. A, B, C, D, N. Yeah. Or I could put primes everywhere. Yeah. Okay. So recall that if G is M generically solvable, there exists a unique M vector relation configuration on G. Now this white core, it's not hard to see that it's M generically solvable. And so as I already illustrated, we can solve for all of the vectors which decorate its solid vertices. And so now what I'm going to do, since my blob's boundary vertices are connected to solid vertices in my vector relation configuration, I can just identify this vector here with a vector that I just sort of push across to the blob. So that's how I'm going to get vectors on my blob. So this allows us to associate vectors to, let's say, to the P boundary vertices of each output disk, and which I'll view as an element of the Grassmannian of M-planes in P space. And this star is giving me the order in which to write down my vectors. Okay, and so on the level of vectors, what I get, so here I could have one or more blobs. In this picture, I only have one blob. But the point is that given my starting configuration of generic vectors around the boundary of my core, I can uniquely solve for the interior vectors and then sort of push them onto the boundary vertices of the blob, which gives a map from the boundary Grassmannian to a product of interior Grassmannians, and in the other direction gives a map from rational functions on Grassmannians. If there are S output disks with P1 through PS boundary vertices. Okay, and I should say there are some details that I am sweeping under the rug. For example, with a vector relation configuration, when it's uniquely solvable, what I get at every black vertex is a one-dimensional subspace. So to identify this collection of one-dimensional subspaces with an element of the Grassmannian, I have to make a choice. And I want to make a good choice of representative. OK. All right. So yeah, so there's some details that I'm not really explaining. OK. But now, in this example, I've worked out what are my vertices, my vectors at the interior black vertices of my core. And so in my small example, I can write down what my map is. OK. And where this is headed is the fact that there are many nice examples which are compatible with the cluster structure. Okay, so if we call this example number 1, let's continue example number 1. We've only got, yeah, and this is also example number 1. What we get, a map, it's a rational map from GR4n to GR4 comma P, and a map in the other direction on rational functions on these Grassmannians, and it's induced by a substitution on vectors where, okay, so really, okay, let me not write it down, but I'll just say it's induced on a substitution by a substitution of vectors using these formulas for VB1 and VB2. Okay, and one can write it down in terms of Plücker coordinates as well. Okay. The theorem is that psi is a cluster quasi-homomorphism, meaning that it's compatible with the cluster structure. So it'll take a cluster variable to another cluster variable up to a Laurent monomial in frozen variables. Okay. And we have many such examples. So our forthcoming paper has a whole bunch of examples. I'm writing down 3 of them. So our motivating example was something called BCFW promotion, which looks like the picture that I showed up here, but it has 2 different blobs. And this is for m equals 4. Another example that you can write down for any m is what we call unary star promotion, and unary means we only have 1 blob, and this is for arbitrary m because this graph over here, well, this graph over here, if you know Plabic graphs, is move equivalent to a star, like a single white vertex with m plus 1 emanating spokes. This is another example. This is also for m equals 4 that we call unary spurion promotion. It's also related to the whole amplituhedron setup. I tried to make my blob look a little bit cake-like. Those are my vectors are replaced by candles. So let me just say a few words about what this framework buys us. Okay, so the theorem is that these maps are all compatible with the cluster structure, which means that we get some cool applications. So the cluster structure on Grassmannians is really poorly understood. We don't have a parameterization of all cluster variables, but by building these kind of complicated maps, we can prove infinite families of new functions which are cluster variables, which were not known before. So that's the kind of application that falls out. And in the case of BCFW promotion, well, we used the analysis of the map that comes from this diagram to do 2 things. One was to show that each way of iterating the BCFW recurrence gives a tiling of the tree amplituhedron. Okay, so this was work that was with Even-Zohar, Leclerc, Parisi, Sherman-Bennett, Tessler. This was I think the conjecture 2 that Pasha talked about yesterday. And the other thing that we were able to do using this approach was show that the cluster adjacency conjecture holds, i.e., so I mentioned this already, if one writes down the BCFW recurrence in momentum twistor coordinates, then all poles in a given term are compatible cluster variables for GR4n. And this kind of thing had been conjectured by physicists and was used by them as a kind of ansatz, because as you sort of take n to be larger and larger, if your number of particles is larger and larger, it becomes more and more impossible to write down explicit formulas. But knowing that the poles are compatible cluster variables as opposed to arbitrary functions on the Grassmannian narrows down the space where you're looking considerably. So I will stop there, and happy birthday, Rick.